Right now, as you watch this, there is a photograph sitting inside a telescope's data server, and in that photograph is the oldest thing any human being has ever seen. Not old like ancient ruins. Not old like dinosaur bones. I mean ancient in a way your brain physically cannot process. We're talking about light that left its source 13.5 billion years ago. Light that was born when the universe was a toddler, barely 280 million years old, only 2% of its current age. That light crossed billions of light years of expanding space, getting stretched, getting redder, growing ancient, and then, in April 2025, it landed on the mirror of the James Webb Space Telescope. What it revealed didn't just break records. It broke our models. It broke our timeline. And it may be breaking our entire understanding of how the universe works. Scientists called it a cosmic miracle. They called it the mother of miracles. Its name is MOMZ14. And the more we look at it, the more it raises a terrifying question: what if everything we thought we knew about the beginning of everything is wrong? The farthest thing we've ever seen. To understand why MOMZ14 matters so much, you need to understand what it means to look far away in space. When you look at a star, you're not seeing it as it is right now. You're seeing it as it was when the light left it. The sun you see every morning, that's the sun from 8 minutes ago. The nearest star beyond our solar system, Proxima Centauri, you're seeing it as it was 4 years ago. Now scale that up. Way up. Light travels at about 186,000 miles per second, the absolute speed limit of the universe. Nothing moves faster. And yet the universe is so incomprehensibly vast that even at that speed, light from distant galaxies takes billions of years to reach us. When we point our telescopes at the deep sky, we are not just looking across space. We are looking back through time. The universe is approximately 13.8 billion years old. For the first few 100 million years after the Big Bang, there were no stars, no galaxies, just a hot, dense fog of hydrogen and helium. Cosmologists call this the cosmic dark ages. The universe was opaque. Light couldn't travel freely. Nothing could be seen. Then, slowly, gravity pulled gas clouds together. The first stars ignited. Their ultraviolet radiation began blasting through that fog in a process called reionization. For the first time in history, the universe became transparent. Light could move. Structure could begin to form. This is what astronomers call the cosmic dawn, and it's the moment they most desperately want to observe. Until recently, the farthest galaxy we had ever detected was called Jade's GS Z14-0. Spotted by JWST, it had a redshift of Z equals 14.18, meaning its light was emitted when the universe was just 290 million years old. Scientists were already staggered by that discovery. 290 million years. The entire history of life on Earth spans about 4 billion years, and here was a galaxy blazing away before even 300 million years had passed since the beginning of everything. Then a team at MIT's Kavli Institute was combing through existing JWST data and spotted something suspicious. An object appearing in infrared wavelengths but completely dropping out at shorter wavelengths. That dropout pattern is the fingerprint of extreme redshift, a galaxy so far away that its light has been stretched far beyond the visible spectrum. They pointed JWST directly at it. They used its NIR-SPEC spectrograph to dissect the light into its component wavelengths. The result: redshift Z equals 14.44. Confirmed. Official. Record-breaking. MOMZ14, the mother of miracles, is now the farthest galaxy humanity has ever observed. Its light left it just 280 million years after the Big Bang. At that moment, the universe was roughly 2% of its current age. To put that on a human scale, If the entire 13.8 billion-year history of the universe were compressed into a single calendar year, the Big Bang happens on January 1st, MOMZ 14 existed on January 7th. The dinosaurs didn't arrive until December 25th. You and I showed up in the final 10 minutes of New Year's Eve. And somehow, we built a machine that can see it. Why MOMZ 14 shouldn't exist? Here's where things get uncomfortable. MOMZ 14 isn't just remarkable because of how far away it is. It's remarkable because of what it is, and what it is, according to every model of early universe formation we have built over decades, shouldn't be possible. Let's start with size versus brightness. MOMZ 14 is tiny. It spans roughly 240 light-years across. For comparison, our Milky Way galaxy is about 100,000 light-years wide. That makes MOMZ 14 approximately 400 times smaller than our home galaxy. It is, cosmically speaking, a dwarf. And yet it blazes. MOMZ 14 is extraordinarily luminous for its mass and size, far brighter than our models predict any galaxy that small should be at that early stage of cosmic history. Our simulations of early galaxy formation have been carefully constructed and refined over decades. They are grounded in physics, in observation, in mathematics. And they consistently fail to explain what we are seeing. This is not a new problem for JWST. Since it began science operations in 2022, the telescope has found galaxy after galaxy in the early universe that is too bright, too massive, and too chemically evolved for its age. Scientists have begun calling this the impossible galaxy problem, though that's a slightly dramatic name for something more accurately described as a deep, growing crisis in our cosmological models. MOMZ 14 adds another layer to that crisis. When the MIT team analyzed its light spectrum in detail, they found something beyond just excessive brightness. They found an unusual chemical signature, a high ratio of nitrogen relative to carbon. This is not what you expect in a freshly formed galaxy at the cosmic dawn. But it is eerily familiar for a different reason. We see the exact same nitrogen to carbon ratios in globular clusters. Globular clusters are some of the oldest stellar structures in the known universe, dense, spherical groups of tens of thousands to millions of stars, tightly bound by gravity, found orbiting the outer regions of galaxies. We've always assumed they formed in the first few billion years of cosmic history. Not the first few 100 million years. Not before the universe was even 300 million years old. But if MOMZ 14 already displays those chemical fingerprints at just 280 million years post-Big Bang, then globular cluster formation may have begun almost immediately after the cosmic dawn, far earlier than any model predicts. That rewrites the timeline in a fundamental way. And the question then becomes, what process is producing this? What mechanism in the early universe is driving star formation that is faster, more efficient, and more chemically complex than everything we've modeled? Is it dark matter playing a role we've underestimated? Is there some feedback mechanism in early black hole formation? Or is it something we haven't even conceived of yet? The honest answer right now is, we don't know. But MOMZ 14 is not alone in asking that question.
A universe that defies its own rules. The thing about MOMZ 14 is that it is not an anomaly. It's a pattern. Since JWST opened its eyes to the universe in 2022, the scientific community has been quietly, and then not so quietly, grappling with a growing list of galaxies that don't fit. Galaxies too massive to exist at their observed age. Galaxies too luminous for their size. Galaxies with chemical complexity that should have taken billions of years to develop, yet somehow appeared in the universe's first few 100 million years. Our standard model of cosmology, called lambda CDM, or lambda cold dark matter, has been the dominant framework for understanding cosmic structure formation for decades. It is an incredibly successful model. It explains the large-scale structure of the universe, the cosmic microwave background, the distribution of matter across billions of light years. It has made predictions that were confirmed again and again. But JWST is now finding things that LAMDA-CDM struggles to accommodate. And the discomfort in the scientific community is real. Some researchers have proposed that the discrepancy comes from our assumptions about how efficiently early galaxies convert gas into stars. Standard models assume a relatively low efficiency. Most gas doesn't immediately become stars. But if early galaxies were converting gas into stars far more efficiently than assumed, you'd get brighter, more massive galaxies forming faster. A tweak to this parameter could, potentially, ease the tension. Others point to early supermassive black holes. Black holes at the centers of early galaxies can generate enormous amounts of radiation that compress gas clouds and trigger star formation at extraordinary rates. If the first black holes grew faster and more aggressively than our models assume, they could be the engine behind these surprisingly luminous early galaxies.
And then there's a more radical set of ideas, ones that don't just tweak the parameters of existing models but challenge their foundations. Some physicists have proposed that dark matter itself may behave differently in the early universe. Most models treat dark matter as cold, meaning its particles move slowly, clumping gradually under gravity. But there are alternative models involving fuzzy dark matter or warm dark matter that could create different patterns of early structure formation. A different dark matter behavior in the universe's first billion years could, in theory, seed galaxy formation earlier and more efficiently. And beyond all of these, some researchers are now asking whether something is fundamentally off in our measurements. Whether the Hubble tension, a well-documented discrepancy in measurements of how fast the universe is expanding, is actually a symptom of a deeper problem with our understanding of cosmic history. What JWST is doing, galaxy by galaxy, redshift by redshift, is not destroying cosmology. It is stress testing it. And right now, several of the seams are beginning to show. MOMZ14 is not the last galaxy that will challenge us. The team that found it said it plainly: the record will fall again. It's not a question of if, only when. Are we living inside a black hole? Here's where the story takes a turn that sounds like science fiction, but isn't. Alongside the MOMZ14 discovery, another piece of research has been quietly causing ripples in astrophysics circles. A study found something strange about the way galaxies rotate. Not just one galaxy, not a local cluster, but a statistically significant majority of galaxies across large survey data appear to rotate in the same preferred direction. In a truly random universe, this shouldn't happen. Galaxy spins should be roughly evenly split, with no overall preferred axis. The universe, according to the cosmological principle that underpins all of modern astronomy, is isotropic, meaning it looks the same in all directions, with no preferred orientation. But the data suggests otherwise. This so-called cosmic anisotropy, a directionality to the universe, is exactly the kind of observation that could point to something deeply strange about how our universe formed. And one of the most intriguing explanations being discussed is this: our universe may exist inside a black hole. This idea is known as black hole cosmology, or Schwarzschild cosmology. The basic premise is this: when a massive object in a parent universe collapses under gravity and forms a black hole, it creates an event horizon, a boundary beyond which nothing can escape. But what happens inside that event horizon? Physics as we understand it breaks down. A singularity forms. Or, and here is the key idea, maybe it doesn't. In extended theories of general relativity, particularly Einstein-Cartan theory, there is a property called torsion that accounts for the intrinsic spin of particles and can influence spacetime curvature. Some physicists have proposed that at extreme densities, this torsion effect generates a repulsive force that prevents a true singularity from forming. Instead of collapsing to an infinitely small point, the core of a collapsing black hole rebounds, a big bounce. And that rebound expands outward, giving rise to a new universe on the inside of the event horizon. In this model, the Big Bang wasn't an explosion from nothing. It was a birth. A new universe expanding inside the collapsed core of a black hole in a parent universe. The rotational alignment of galaxies would then make sense. Our universe inherited its spin from the rotating black hole that birthed it. That spin is baked into the fabric of spacetime itself, and it shows up in the way galaxies align as they form within it. This framework, if correct, would also carry a staggering implication. Every black hole in our universe could be the seed of another baby universe. An infinite, self-replicating cascade of universes, each born from the collapse of stars in the one before. The fundamental constants of nature, the specific values that allow matter, chemistry, and life to exist, would be explained not by chance but by a kind of cosmic natural selection. Universes that produce stable black holes reproduce. Universes that don't. It remains a theory. It remains speculative. But it is mathematically consistent, it explains several anomalies, and it is the kind of idea that JWST, by peering further back into cosmic history than ever before, is now giving us the tools to either support or rule out. We built a telescope to look at the beginning of everything. And what we found is raising the possibility that the beginning of everything was itself born from something else. The universe is stranger, older, and more recursive than we ever imagined. And we are only just beginning to see it.